Welcome everyone, and thank you for joining us this afternoon for this webinar. My name is Laura Roberts, and I'm the Ava Marketing Manager for PDS Group. For those of you who may not be familiar with PDS Ava, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. Today's session is presented by Vicky O'Connor, the Ava Subsurface Director. We will explore how quality data blended with scientific methodologies can lead to increased confidence in volume ranges by using our Ava Clastics and Ava Saturation modules. Before we get started though, a quick note on housekeeping. There'll be time at the end of the webinar for questions and discussion. If you wish to ask questions, you can type them in the question box at any time during the webinar, but we'll only answer them at the end of the session during the Q&A. Alternatively, if your question requires a little more explanation, please use the raise your hand function and I'll turn on your microphone so you can ask it verbally instead. Please also note that our webinar sessions are recorded. Now, without further ado, I'll turn the time over to Vicky. But Vicky oversees the product commercialization of PDS's geoscience services. She holds an MSc in Geoscience from the University of Liverpool and has 10 years experience in the oil and gas industry.
Great, thank you, Laura. So she's nodding at me, which means that I'm online and hopefully you all can hear me. Right, so thanks everyone for taking some time out of your afternoon or morning, wherever you are, to dial in today. As Laura introduced, I'm going to basically discuss how we can combine high quality data along with some different reasonably cutting edge scientific methodologies to investigate a couple of different types of uncertainty using some of our Ava technologies as a basis for doing that. So I'll touch upon a couple of slides in terms of just subsurface uncertainties, which should be a little bit like preaching to the choir for most of you. Then we'll take a look at, just by way of introduction, how we investigate facies variability using analog data with our Ava Clastics technology. Then I'll switch to talking about saturation modeling and how we have different methods available for that in our Ava Saturation technology. But we'll spend the main part of the session actually looking at a case study for this Ameland field, which is in the north of the Netherlands. And what I'll do there is I'll show you how we can use our two technologies to draw upon analog data, blend that with some saturation height functions that we create through Ava Saturation, and apply that to a model that we've already built for the Ameland field in order to start investigating the uncertainty around the gas in place for that particular asset. I'll try and keep all of that to about 40 minutes max, so that should leave us with a good bit of time for Q&A and any discussion at the end. And as Laura said, you can raise your hand or just type in that chat box as well as we go. Okie dokie, so first off then, so just again, if you're a reservoir modeler, you'll know all this already, but obviously there are various uncertainties in the subsurface, and what we are basically trying to do when we are doing any kind of subsurface evaluation is kind of identify what are really the key uncertainties related to our specific asset. And then ideally, if we have the tools and the time, we are always wanting to develop kind of multiple but plausible scenarios that will help us test and investigate those key uncertainties in particular, and the impact that that has in terms of either volume range or recoverable volume or whatever. So there are different subsurface uncertainties, and they can affect things like the GRV, the in-place volume, and the recoverable volume. And some of them are kind of displayed on the right-hand side there. But what we're going to do today is we're going to investigate two particular uncertainties. So facies modeling, or 3D facies variability in the interwell space, which obviously affects the in-place volume. So we're going to look at how we can leverage analog data to help us distribute the 3D property or multiple 3D properties of facies in a more sensible way to basically have multiple but plausible depositional scenarios that we can use as a basis for other calculations. We'll also then look at saturation modeling. Again, it affects the in-place volume, and I'll just show you how we can create a couple of different saturation height functions, varying either the method used to derive the function or the input data that we have available to us. And we can, along the way, discuss whether things like, is there a right function or for a particular model. So we'll kind of cover those two areas, and then I'll blend them towards the end of the case study. Okay, so this is just a quick 5-minute overview of our approach at PDS to trying to leverage high quality analog data into facies modeling. So apologies if some of you know this already, but just to recap. So essentially, I think it's pretty well established in the industry that there is this ideal idea that you can compensate for the sparsity and the locational bias of your well data with sensible application of analog information. So that's something that people have been trying to integrate into their geomodeling workflows for a long time, and they also bring it into their exploration workflows as well. But one of the big challenges you face doing this, well, two challenges you face really put a bit of a block on doing this in an effective way. So firstly, it's difficult to access and then explore for suitable analogs for your particular asset. So finding a data source which is rich enough and well structured enough to actually be of any use is a challenge. And secondly, if you are able to identify an analog that you might be able to use, the conversion of that analog data into parameters that you require to drive things like facies modeling algorithms is not always accessible, and it's not always easy. So what we advocate to address that is the use of really sophisticated high quality relational databases, which are populated with a combination of data derived from both modern and ancient systems. And I'll discuss that in a bit more detail. But this is the kind of thing, these are the kind of input data sets that you need to start converting that data into something useful you can use for facies modeling. So you'll see many more charts like this as we go on. So as part of our Ava Clastics product, we have a partnership with the University of Leeds, who are world-leading sedimentologists, and actually they've got quite a myriad of research groups at Leeds. And we collaborate with 3 of them, so the FRG, the SMRG, and the TRG. And those groups, all 3 of those groups, for a long time have been looking into the problem of databasing, or it's not just databasing, but capturing the key elements from these different clastic depositional environments and systematically characterizing them for use in research applications in their world. But we work with them to bring the data that they're compiling in these various databases in the different research groups to create a product which is more useful for end users in commercial organizations. So this really started off at Leeds as an academic effort, but they quickly realized, as did the sponsor companies for the different research groups, that there was a commercial application for a lot of these databases as well. So we leverage that in Ava Clastics, and you'll see how that works in the demonstration. There's a whole, I could talk for an hour about the structure and architecture of the databases from Leeds, but just to point out a couple of the highlights really. So there are probably 2 things that are very special about these databases. Firstly, that they're hierarchical. So as you can see on the screen in the graphic, there's a link between the coarser scale depositional elements, so things like channel complexes, right through the architectural scale and down to the facies scale. And they've linked all of these different elements at these multiple scales, which is really nice because it can allow us to do things like hierarchical modeling inside Petrel. So modeling the depositional elements using one modeling approach and then the architectural elements in another way, for example. They also contain, all these databases contain transitional information as well. So they record statistics on the links between different element types. So they have lots of statistics around or that you can derive from that calculate the likelihood of encountering one element type versus another laterally or vertically or down dip in different depositional environments. So we can leverage these very high quality relational databases in things like object modeling, but also in variogram-based facies modeling algorithms and beyond. So the other aspect to dealing with analog data. So it's not just having access to the data itself, it's actually parameterizing as well. So this is just a couple of examples from object modeling or variogram-based modeling. And in the little yellow boxes, you see the kinds of input parameters that you need to derive or need to have available to you to actually calculate something meaningful with those algorithms. So what we are trying to do with the databases is we've developed a logic which takes a subset of the data in the database and converts it directly into a particular set of inputs for a particular facies modeling algorithm. And again, you'll see that in action in a few minutes. Okay, so that's giving you a flavor of what we're doing with the analog data in Ava Clastics. Switching briefly to Ava Saturation, just for a recap for those of you who don't know. There's obviously uncertainty in saturation modeling. It's one of those weird tasks that falls between, its ownership falls a little bit between the geomodeler and the petrophysicist and the reservoir engineer, but obviously it's a critical task, which is absolutely essential for deriving certain things like in-place volumes. So it's an important task, but there are lots of uncertainties that crawl in the way that from the logging tools to the free uncertainty in the free water level, all these kind of things. And on top of that, unfortunately, it's done in a really ad hoc manner. So today, lots of people geomodelers in particular, get stuck doing saturation modeling are copy and pasting algorithms from an email that they've got from a petrophysicist and all this kind of stuff. So it's not done in a very optimal manner at the moment. And also on top of that, there are a whole bunch of different approaches. So there are many different algorithms that are available, somewhat dependent on the type of input data you have, but there are quite a few formulations that you can use to derive a saturation height function for application to a 3D model. So there's uncertainties in this. It's not really often owned by anyone, and there are a few different approaches. So what we try to do with our technology, as you'll see, is we've started to implement a few different calculation methods, and we've essentially created a guided workflow for people doing saturation modeling, saturation height modeling, to make it really efficient to firstly identify the information that you need to actually undertake the calculation. Secondly, to go about isolating the region or sub-region of the asset that you want to apply that saturation height function to. And thirdly, we automate the application of that height function into the 3D grid and provide an audit trail around it as well. So just by way of background then, we offer a couple of different functions. The Cardifor one, the formula, the resultant function is shown there. We also offer the Skeller-Harrison method as well. And if you have core data available and some scale measurements, you can actually derive a leverage function as well. So that's what we currently have today. So that was just some background in case you guys haven't seen much of our two Ava products before. But what we're going to do now, because it's a bit more fun, is actually look at a case study. Okay, so we're going to take a look at the Armelin field. So I'll give you a couple of slides by way of introduction, and then we'll take a look directly in Petrel in the products, and let's take a look around the data that we have available. So just by way of introduction, the Armelin field, or collection of fields, is up in the north of the Netherlands. And when it was discovered, and subsequently, it was the third largest gas field in the Netherlands at the time. So it's a pretty sizable asset for the Netherlands. And it's Rotliegend group reservoir predominantly, in this particular area anyway. And the upper Schlockturn is the target sandstone for this study anyway. And we'll talk a bit about the depositional setting for that group in a second. And also there's, as you can see on the map on the right hand side, there's a whole bunch of north, northwest, south, southeast and corresponding perpendicular faults, which kind of subdivide the field into a bunch of fairly major fault blocks, which you'll see in 3D in just a second. So in terms of the depositional environment then, if you dig around the literature, you can find that there's some discussion or debate about the depositional environment. So it's thought to be predominantly fluvial in this particular area. And there's some discussion about whether the fluvial systems are ephemeral or perennial. So what we can do is we can just take those two ideas, and rather than spend a long time worrying about whether they'll actually make a difference to the volume calculations, is we can just look directly in Ava Clastics and see what kind of geometries and kind of data we have for those two alternative depositional environments or sub-environments. So in the cross plots you see there, these are just simple cross plots of thickness versus width for the ephemeral versus the perennial sub-environments. And this is at the middle scale in the database. So we're looking at the what's called the architectural scale. And you can obviously see that there's quite a significant difference in the distribution of certain element types in those two cross plots. And we'll see some of this data live in Ava in just a sec, but just to show you some of the other representations as well. So this is looking at proportions chart. So again, there's quite some difference between the proportions that we see in the ephemeral versus perennial. Yeah, that's fairly clear to see, I think. But still, you know, the aggradational channel fill is dominating quite substantively. And then we'll also take a look at these charts in Ava as well, I think. So we can also, I mentioned briefly when we were doing the introduction that one of the neat things about the database is that they store data which basically maps the lateral, vertical or down drip transition between elements. So these charts are trying to represent a aggradational channel fill in the center, and then looking out vertically, laterally or down dip, which other elements in these sub-environments this aggradational channel fill is likely to encounter. So we'll take a look at that again in Ava in just a sec, but just so you can kind of see that there's a subtle difference between the two charts, which is showing us that in these different sub-environments, we expect different connectivity between different elements, laterally, vertically, and down dip. And we can explore that in more detail. And so in terms of the saturation concepts, so as I mentioned, we have a couple of different approaches available. Unfortunately for this field, we don't have any core data, so there's no measurements that we can use, so we have to rely on the logs in this case. But what we'll do is we'll create a couple of different saturation height functions, just using a couple of different methodologies and see if it actually makes a difference. In our case, a substantive difference to the output gas in place. And this is just an example of the kind of functions that we'll derive, but I'll skip over this because we're going to see it in Ava in just a second. Okie dokie, so hopefully everyone can see this. Laura's given me the nod, great. So now we've jumped into Petrel. This is, and I'll explain how Ava is connected in a second, but what you're looking at is an upper Rotliegend surface and the well penetrations for the field. So you can see these is a bit of a rough surface, so forgive us for that, but you can see these fault blocks that are sort of starting to emerge. Okay, so what I'm going to do now is I'm going to run through the Ava Clastics part. So we're going to go into Ava Clastics, look around for this ephemeral data and isolate the analogues based on that filter. Have a look at the data, and then I'm going to show you how you can take that query and cascade it through to a 3D facies distribution. Then we'll do something similar for Ava Saturation. So we'll collect up the relevant log data that we need, derive a saturation height function using one of the methods, and then apply that in 3D too. And then we'll actually have a look at, firstly in the well section window, to kind of explore these different, what the different analog subsets and saturation height functions, what that looks like in section view compared to the logs. And we'll also at the very end look at how it impacts the volume ranges as well. Okay, so first things first, let's open Ava Clastics. So as Laura mentioned right at the beginning, Ava Clastics is, or all our Ava products are software as a service, which might not seem very interesting or very important, but it allows us to do some kind of neat things. So what you're seeing on the screen here is essentially a web-hosted technology, which you could also just open in a Google Chrome browser. So you can do this, what you're about to see on the screen, up until the very last stage where I link it to the objects in Petrel. All of this you can do in a web browser separate from Petrel, or even on your phone if you really feel that way inclined. And one of the neat things about being online is that it's personalized, and you'll see why that's important as we go through. Okay, so the first thing I want to do is come into the Explore area and isolate the data of interest. So as I mentioned, we work with the team at the University of Leeds, and we actually make 3 different databases available covering fluvial, shallow marine and deep water environments. In this case, for the Upper Schlockturn Tieren, we're interested in the fluvial database and specifically some sub-environments in FACS, which is the fluvial database. So we'll have a look at those and I'll show you some of the data representations again, just that we were seeing in the other view as well. So here we're just looking at a very basic cross plot. So this is the data that if you start searching around for analog information in papers, this is the kind of thing you see. So thickness versus width charts. Now there's lots of overlap, but this is because we're looking at all the data that's available in the database. I haven't filtered it in any way. So this is all fluvial, all the thickness and width information from all the fluvial analogues that we have access to in FACS. You'll see how it changes as I filter it in just a second. Coming down, so this is the same chart type, but in this case we're looking at what's called the architectural scale. So this is now looking at individual channels, levees, crevasse splays and things like that, coal bodies and whatever. So sort of coming down a scale. And then finally we also have information on the facies scale as well. We don't leverage that in the modelling workflows at the moment, because it's not really the sort of the normal geomodeling scale, but we do have all the data available in the database, so you can take a look at that. Let's just pause at the architectural scale for a second though, and I'll just flick through the other chart types that you see. So here we're just looking at histogram, again, of all the different element types. Again, this is for the whole database, so I'll pause in a minute and just interact with some of the filters so you can see how that looks. This is the pie chart representation again, so looking at the proportions of different element types. Here's that transition chart that we were looking at before in the presentation, and you can just pick a particular element type. Again, this is for all the data in the database. I'll filter it in a second. But here we're looking at an aggradational channel fill, and if I just click on the portion of the donut which is lateral, it'll expand, and I can have a look at that and see that if I'm going laterally across all the data available in the database, this is the sort of the likelihood of the other elements I'm going to encounter. So laterally accreting macroforms, aggradational channel fills, and bank fines are kind of the predominant elements. But let's just interact with some of the filters now. So we were talking about what we're looking at for ephemeral. So there's a couple of different options. So you can combine filters as well. So if you want to apply a paleoclimate filter or look for a different depositional setting, you can start adding and building up a combination of filters. But for the sake of this demonstration, I'll just show you something quite simple. So I'm just going to filter by ephemeral data in this case. Okay. And for those of you with a keen eye, you will see that the transition chart is updated in terms of the likelihood of things that are connected in these different directions. And I could also go in and do the same thing for perennial if I wanted to. And again, we've got an update in the chart there. But let's just run with our ephemeral example for the moment. So what you do essentially is you use this canvas to identify or isolate a subset of the analog data in a particular database. And then we move to the next stage, which is what's called creating a depositional concept. And a depositional concept is basically a combination of the analog data that you've isolated in the previous step with what we're about to do, which is expressing that or converting that analog data into a format that can be used in a facies modeling algorithm. So what I'll do here is I'll just give this a quick name. I can spell ephemeral, there we go, example. And I can just provide some supplementary information. I can also, if I wanted to, expand here and see a recap of the charts that I was using in the previous step. But more importantly, in this step, you can come down now and start converting that analog data into a format ready to go to drive a facies modeling algorithm. So what we do is we give you a choice of different algorithms. So for the fluvial database, these are the two algorithms in Cybertrail that we support. These vary in different environments. So for shallow marine environments, for example, we support truncated Gaussian simulation, which is obviously quite heavily used there. But what happens basically is when you make a selection, the view will update as I select these additional elements to model. And the internal logic in Ava will kick in. So it will transform the analog data in the previous step into all the settings required to run object modeling in Cybertrail. So all I need to do now, and this is quite a simple example because I've just picked the depositional element scale, which is your channels and floodplains, so just for the sake of demonstration. But what you'll see here is that all I've done is said, right, okay, at the depositional scale, model these channels. And what's happened is that Ava has gone off and defined a whole bunch of things like the amplitude range, wavelength, and all these kind of things, all the input parameters that we need. There is a little warning because around orientation, because obviously Ava doesn't have the information to predict or know what the orientation will be in your particular asset. So you do have to fill that in. But otherwise, these other input parameters are derived for you. So in this case, I'm just going to say model the channels and the floodplain as just a background facies. And if I go ahead and save that now, what will happen is that it will save it into my library of depositional concepts. So this is when the personalization of the products becomes really sort of useful. So here, for example, you can see that I've been creating a whole bunch of different examples, depositional concepts, and some of them have this little logo next to them, which implies that I've shared them with one of my colleagues as well. So you can share these concepts within your own organization, people. So this is me sharing it with other people in PDS. Okay, so I've created an ephemeral example. You can see I've got perennial one here and an ephemeral one I made earlier. And we'll look at some of the results from those in a second. But just to show you the final part of how we then map that into a 3D property in Clastics. All we have to do is select our final kind of grid icon. And as I say, everything up until this point, you could have done this all in a browser. You don't need to be in Patrol. But for this final step, you do. So you select a 3D grid. You can create a new property, or if you happen to have upscaled cells, which I do in this case, I can select those. So what that will do is it will mean that when we run the facies modeling algorithm, it will honor the upscale, the proportion, well, the facies code in the upscaled cells at the well locations. So the final step then is to map a particular depositional concept to a particular zone, which I can do here. And you have to inform it about the templates because, well, just a patrol thing. Okay, so now we're going to run it, and we'll look at how some results in just a second. But what's happening now is that Ava is reaching out and building a connection to the facies modeling process in Patrol, and it's automatically populated, in this case, zone B, with the proportions and the thicknesses and all this kind of stuff. All the parameters you see here at the bottom are all informed directly from that previous step in the depositional concept. So if I say OK, it will just run, and it will create a new property in the 3D view that we can have a look at. Or even better, we can have a look in the well section window and see what that looks like. Okay. So conveniently, here's one that I made earlier. Patrol's having a moment. So let's just give it a second to catch up. But what you can see is that, so the upscaled, the facies log, the interpretive facies log is here, shown in the track. And in this case, we're looking, and this is the ephemeral example from that I made previously. And unfortunately, my Patrol project has crashed. Apologies for that. But just while that's reloading, let me just show you the results in here anyway. So this is essentially what you're seeing. So apologies for the Patrol logo in the way there. But the ephemeral system is the one I was just showing you on the board. And I've also I've done the same thing, but for the perennial sub-environment. So I did exactly the same, went through Ava Clastics, applied that filter, just that single filter for perennial, modeled at this coarser depositional element scale, and this is the resultant 3D facies distribution. And it certainly doesn't take a genius to see that there's some quite dramatic differences in the overall net to gross, firstly, but also the connectivity in different directions as well. So that's quite an interesting observation. And all we've done there is we haven't done a very complex filtering of that data at all. We've just applied a very light filtering to the facts database in this case. Oh, we're almost there. I'll just reopen the project. So that's a quick look at the facies variability. But what I'll show you now is the derivation of the saturation height function, which will probably take 2 or 3 minutes, I guess. And then we'll look at the results again in a well section window, or maybe in 3D, one of the two. And then we'll take a quick look just to close out by looking at the gas in place that's calculated based on those alternative different sets of scenarios. And I've run a quick uncertainty workflow as well, so we can have a look at how that impacts the distribution of gas in place as well. Cool, so I think this will take us back to our original screen. So apologies for this, everyone. Thanks for hanging in there. Okay, so let me open Ava Saturation then. Okay, so this will look kind of similar to Ava Clastics, as you just saw. So again, it's personalized in the same way. So you can build up concepts in here, a little bit like I was just doing in Ava Clastics. But we'll create one here, and I'll just run through this quickly. Okie dokie. So just giving it just applying it some basic information. And we're just building up this concept basically. Now, Ava Saturation is even more simple to use than Ava Clastics because it's essentially one long guided workflow. So you just work through it, follow the instructions. In this case, I'm going to pick the Armelin grid, and I'm going to pick a particular contact, and I just kind of step through picking certain properties as I go. And I'm basically assembling the input data that I require for the calculation. So I'm going to ask it to focus on zone B. So what I can do here is I can group certain parts of the model both vertically and laterally. So if, for example, I believe that there's a shared free water level across these particular segments and there's consistency in the input well data, then what I can do is group these three segments of the model. And when I'm calculating and then distributing the water saturation property in 3D, it will populate across those three segments together. So, and facies is quite simple in this case. It's just sand and shell. But if I had multiple different facies types, I could group them together here to create kind of a net grouping versus non-net. So I hope that makes sense. Here is when we actually create the function though. So now I'm saying I'd like to work with zone B specifically. I'd like to work with that segment group that I just created in the previous stage. I'd like to apply the saturation height function to the sand facies specifically. And I'm just going to give it a name. Okay. So all it does is produce a little card, and you can see from the scroll bar that we're almost down to the bottom of the guided workflow already. So there's a section here on porosity banding as well. So for those of you that are in the know, you can calculate different height functions for different porosity bands as well, but we won't do that in the interests of time today. But here we have the option to use different approaches. So as I mentioned, we have 3 available. If we try to use leverage J in this case, it won't work because we don't have the capillary pressure data that we need. But we do have the log data that we require to derive based on the Scaled-Harrison formulation. So that's what I'll do now. And what I have to do is tell it which wells to use. So it's smart enough to realise that wells 1, 2, and 3 intersect segments 1, 2, and 3 of the model. So what I can do is, and I can do this interactively, so I can decide that I only want to use these wells. Maybe I want to create multiple concepts with wells 1 and 2 only, another saturation concept with all 3 wells, for example. So you can do stuff like that and do kind of a multi-well analysis quite quickly using Ava Saturation. But here you see the resultant function. Oh no, it's going to crash again, I think. Yes, I think we might crash again. That's very, very annoying. Apologies for that, guys. However, fortunately for you, I do have screenshots of what it's supposed to look like. So I'll restart in a second just so we can see the volumes. Actually, I might have an image of them, actually, so we might not need to. But this is what happens. This is the result anyway. So all I was going to do there is look at that function, which I'll try and get back up in a second. And then there's basically a button at the bottom which says map to 3D grid. You hit it, and it distributes the 3D water saturation property in 3D in that particular zone. And the result is what you can see on the screen here. So in the top right, actually this is both using the ephemeral distribution. So if I look back on the previous screen, so just as a reminder, so the top image on this slide is showing the distribution of sand shale in the ephemeral case. In the upper image here, we're using that ephemeral facies model as the basis, and we're using a Cuddy-4 function in this case, plus wells 1 and 2 to create and distribute the saturation height function. Along the bottom, you're seeing again the same facies model, but in this case we're using the Scaled-Harrison method, which is what I was just trying to do and it crashed there, combined with wells 1 and 2. So you can see there's some variability in the water saturation property that's created, but we still have a good tie to the wells. In both cases, it's fairly reasonable. So let's see if Petrel's woken up. Oh, it has. That's good. So this is the function that we're creating, and you can go in and you can edit this, or you can maybe decide at this point that this type of calculation method is not appropriate based on your input data. So you can kind of go back and forth up along this guided workflow and try out some different things. But let's just assume I'm happy with this. I just say accept function. And then, as promised, I use this little button at the bottom to basically say, please go ahead and apply this function based on this input data to this particular part of my 3D model. And similarly with Ava Clastics, what we do here is we have a bridge with geometrical modeling, and we leverage that basically to apply that saturation model in or distribution in 3D. Cool. And what we do as well is we make this all quite explicit, so we could just run it kind of anonymously and just show you the result. But what we like to show people is that actually these statements are kind of being leveraged through the property calculator, so you can go and actually see the function. If I were to expand this, you'd see the full function written out. That means you have that preserved in Petrel as kind of an audit trail there. Okay. So again, here's one I made earlier, but what we've done basically is created, we have a saturation, Ava Saturation folder here, and it's all time-stamped and everything, so you can see what we've been creating. This is the one I've just made, so which looks the same as the previous Scaled-Harrison one I just made as well. So, but you can kind of see what we're doing. So we're distributing that property in 3D space. So this was the property that I just made in the previous step. Okay, so finally then, just want to show you just for the last couple of minutes how then we can take this through to actually looking at some of the implication for volume ranges and things like that. So what I did quickly was create a couple of volume cases based on, I think in this case, the 2 ephemeral options, but let's just look. If I just look at my cases tab. Oh yeah, okay, so this is for the 2, so this is based on the ephemeral facies model using 2 different saturation height functions. And around that, I just decided to run an uncertainty and optimization workflow as well. So I just did this quickly just to kind of show you how you would go about feeding this information through into something like the UNO manager inside Patrol. So all I did was use my ephemeral Skelton-Halvorsen as a base case, and in this case, I just varied the porosity as a variable and created a bunch of cases with Monte Carlo sampling for that, which basically creates a range that looks a little bit like this. So this is based on 50 cases in this example. But just so you can kind of get a sense of the sort of workflows that you could run once you've created a couple of kind of base case concepts. In the next webinar, actually, we're going to look at this in quite a bit more detail, and I'll do some more advanced uncertainty optimization workflows there as well. And of course, as part of those, I don't know how familiar people are with the uncertainty and optimization manager in Patrol, but obviously you can go and you can create various outputs like this as well. So this is just a volume map. And this is the ephemeral case with the Skelton-Halvorsen saturation height function method applied, and I could switch from that to the option. So again, same facies model underlying it, but in this case using the Cuddy-4 method to derive the height function. So, okay, so apologies for all that trouble with Patrol there. That was a bit annoying. But as promised, I've kept to about 40 minutes. So essentially, just to conclude then, so what I was trying to demonstrate there is that we have an approach which goes from analog databases, which are provided to us by our friends at University of Leeds, and we also include and can combine proprietary data from companies into that mix as well. We take that data, we go through a parameterization internally, so you isolate the analog of interest, we parameterize it, and then we use that in conjunction with the facies modeling algorithm to create a 3D facies distribution. This one is a bit more sophisticated because it's showing the modeling at the architectural scale, so you can see more element types in there. And similarly with saturation, we start from either log data like we did in this example, or you can start from core data if you wish. We combine that with a method, and we've got 3 in there at the moment, but we'll be adding some more as well probably. Basically to collect up the information you need for a particular part of the model, derive a saturation height function, and then distribute that in 3D as well. And these obviously provide you with various inputs that are kind of dependent, which can go into the volume calculation and uncertainty estimation workflow as well. And yeah, these are just some of the additional maps that we're looking at. So obviously, in this case, keeping the facies, just what I'm showing here is the facies model being the same, but a variation in the saturation height function derivation method. But obviously, we could have looked at the change in the facies model as well. And as I say, we'll be doing a bit more of that in the next webinar. Okay, so I think we'll probably close it there and take questions. I guess it's probably just worth mentioning as well. So we do have, as I said, we do have another webinar coming up, and that's going to be more focused around looking at combining structural uncertainty, particularly around full extension uncertainty, with the saturation modeling uncertainty. So probably what we'll do there is look at a couple of alternative plausible structural models that we can create using our Ava structure technology, and we'll combine that with a multi-well analysis. So we'll use different combinations of well data to derive slightly different saturation height functions, pass that through to the volume calculation and uncertainty and optimization manager, and create some more sophisticated uncertainty optimization workflows to look at in that particular session, which will finish us off for the year, I think. Okay, so Laura, do you want to?
Yeah, just to thank you for presenting today, Vicky. It was really great to see how we can use Ava Clastics and Ava Saturation together to improve calculated volumes. So just a reminder that we are now open for questions. So if you wish to ask a question, type it in your question box in the go to control panel, or alternatively, you can raise your hand if you like to ask a question too.
Thanks, Laura. Yep, I'll be online, Laura, for another few minutes. So obviously just feel free to raise hands or type questions or whatever. And alternatively, if you want to just send me a more sort of detailed note or something separate, feel free to use my direct contact details, which are down there on the right-hand side. So always happy to talk about all things facies modelling and saturation height modelling and all that good stuff. So.
Yeah, so it doesn't look like there's any questions right now, Vicky. So just a reminder to everyone, like Vicky said, that she is available for questions offline. Vicky's email address is vicky.o'connor@pds.group. So Vicky, is there anything else you'd like to add now?
Not really, just thank you guys for hanging in there, and apologies for the Betrell issues as well. So I'm trying to, I have a Surface laptop, and that occasionally fails me. It's not quite standard spec for running Betrell, unfortunately. So apologies for that, but hopefully it wasn't too disruptive. And yeah, thanks again for taking the time out of your day to join.
So yeah, a thank you from me also to everyone. We really appreciate you being here this afternoon. Just a reminder that this webinar has been recorded and all participants should receive a copy via email within the next 24 hours or so. If you wish to share that link with your friends and colleagues, please feel free to do so, or alternatively direct them to our website, because we'll be uploading a copy of this webinar to our website also. This was the fourth webinar in our Autumn 2019 series. The final session of our series takes place next month, as Vicky's already mentioned. She'll also be the presenter of that session, and she'll be assessing and quantifying structural and water saturation uncertainties in reservoir models. For details of that webinar and all our past webinars, please head to our website. You'll find the registration on the screen right now, or alternatively simply browse Ava Autumn Webinar Series 2019. We thank you again for being here today, and we hope to see you next time.